Oh, it's good. Good. I'll do that.
Oh, yeah. All right. Thanks, everyone, for coming to the afternoon session for the third day of this workshop. And this afternoon, we're pleased to have Henry Towsner, and he'll be speaking about tameness and hypergraph regularity.
All right. Thank you for having me. So there have been a couple talks about regularity and hypergraph regularity already to some degree, but I think I should still give a little bit of an introduction for people who missed those or just need to see it defined more than once because it's not a simple notion. So all of this stuff builds on Semiretti's regularity lemma for graphs. Lots of people, including certainly Semiretti, usually think of this in the context of finite graphs, but I prefer to think about at least having the option of infinite graphs with some measure theory floating around. So to say this in a slightly general way, I imagine that I have sets X and Y and a measurable subset of X and Y, of X cross Y. And what graph regularity tells us is that for each epsilon, I can partition X and Y so that these rectangles, AI cross BJ, E is mostly random of them. On most of these rectangles, E is epsilon quasi-random. I'll say a little about what that means in a minute. And then there's a small measure of exceptional rectangles. And you get the combinatorial setting back when you say that X and Y should be finite, and the only measure you really care about is the counting measure, where the measure of a set is just the fraction of the total number of points that it belongs to. I should add, often I'm describing here a bipartite graph where E is a subset of X cross Y. Often you would just take E to be a set of pairs from X, but everything gets a little easier to state if you stick to a partite setting, and it doesn't really change anything fundamental. All right, so the picture you should have in mind is you start with a set X cross Y, and you think of it as this big rectangle, and E is the set of points that are in your set. And so here I have something that looks kind of like a half graph, except there's just some slight error to it. Some points are not quite where you think they should be. And what regularity says is I can partition this into rectangles, so something like this, and then on each of these rectangles, instead of talking about the discrete points, I replace them with a density. And what I notice is that in this case, most of those boxes, kind of all the points were there. That's these darker boxes, or none of the points were there. That's the totally empty boxes. And then there are some intermediate boxes. And furthermore, regularity promises that in most of these boxes, what's going on inside is quasi-random, and I won't get into what that means. The important picture here for us is this decomposition into these boxes where we can replace the specific information of which points were present with this kind of approximate information of how dense were the points in this box. So there are two sort of well-known facts about this. One is that in general, the partition you need might be very large. In fact, it's a theorem that Gowers that you really might need a tower of exponents of size on the order 1 over epsilon. So really a very large number of pieces. And you can't avoid the possibility that there are these bad rectangles that fail to be quasi-random. So there's been this line of research connecting the combinatorics to ideas in model theory on what would it take to fix some of those issues, to get nicer partitions. So a graph has finite VC dimension if it omits some small bipartite graph. So there's some bipartite graph G on sets V and W, and you should think of maybe V and W are finite when X and Y are infinite, or V and W are small when X and Y are large. And there's no induced copy of this graph G. So for example, the half graph, which of course keeps coming up, is you could think of as the set of E on, say, the unit square, 0, 1 cross 0, 1. And E consists of those pairs X and Y where X is less than Y. And this has finite VC dimension because it emits this small graph here, right? I can't have an X1 and an X2 in the X side and a Y1 and a Y2 in the Y side, where X1 is less than Y2, but not less than Y1, because there's an edge between X1 and X2, but no edge between X1 and Y1. But also the reverse happens with X2. That's not consistent with having the ordering. So so what we might call, I mean, I think probably most people here know this, but just to be explicit, right, having finite VC dimension is being an NIP, is NIP as a relation. So a theory is NIP if every definable relation has finite VC dimension. So this is sort of a classic model theoretic dividing line. So this theorem shows up kind of not very explicitly in Lovász and Szegedy, and other people may have noted it in other places because it's not that hard to prove from kind of the underlying theory. If your graph has finite VC dimension, then when you make these partitions, most of them are either all in or all out. So if you remember the picture I showed of you a while back, you notice that there aren't really any partition. There are only a few partitions along this diagonal where the color is an intermediate shade of gray. Most of these boxes are either empty or full. And well, that was the half graph. It has finite VC dimension. And so Lovász and Szegedy showed that's always going to happen. If you have finite VC dimension, most of your rectangles either have density close to 1 or density close to 0. They're either all in or all out. And you might have, like the half graph does along the diagonal, a small set of intermediate density. And one way that I find is very useful to think of this is this actually tells you that if you have finite VC dimension, you're close to a union of rectangles. Because you could just take all the rectangles where the density is close to 1, and you take the union of those, and that's very close to E. You've thrown, those rectangles might not have density exactly 1, so you've thrown in a few points you shouldn't have thrown in. You omitted the rectangles with intermediate density, but there weren't very many of those. So if you have finite VC dimension, you're approximately a union of rectangles, which is exactly what I'm saying here. When E has finite VC dimension, E can be approximated by a union of finitely many rectangles. All right, so another dividing line is stability, maybe I guess the dividing line with stability, right? So being stable is stronger than having finite VC dimension, because finite VC dimension, you omit some bipartite graph, and you're stable if you omit a specific family of bipartite graphs, namely, well, one way to state this is say you omit the ladders. You omit the graph where you take finite sets for X and Y, and you think of them as the interval 0 through N, and you omit the set of pairs where I is less than J. And Malliaras and Schlaw showed that that when your graph is stable, you have a yet stronger property that you get a partition where every rectangle has density close to 0 and close to 1. So in general, with finite VC dimension, you might have a small number of bad pairs, bad rectangles where your density is intermediate. Malliaras and Schlaw show that if you're stable, that doesn't happen. You can actually end up having every single rectangle be close to 1 or close to 0. So I sometimes like to say, so being stable says not only are you approximately a union of finitely many rectangles, but there aren't these intermediate rectangles. All right. The standard example of something with finite VC dimension that's unstable is exactly the half graph. And this is exactly the example where you can try to approximate it by rectangles, but you can't avoid the fact that that you have that messy diagonal, and that diagonal is always going to force you to have some rectangles with intermediate density. Right, so this is what happens if you try to partition into rectangles. And you can try to partition it into more rectangles, but you can't avoid this possibility that you get this stuff along the diagonal. Apparently I kept going. Okay. All right. So just as an aside, there's also, as it turns out, a distal regularity lemma. So Chernikov and Starshenko showed that if you're distal, you might still have those intermediate rectangles, so you have a small number of intermediate rectangles, but on the rectangles that are not intermediate, you don't just have density close to 0 or density close to 1, you're actually homogeneous. You're either all in or all out. I'm not going to say much more about that, but just sort of these are, distal is a different strengthening of finite VC dimension. Right, so finite VC dimension says you have a small number of bad rectangles, but then otherwise you're close to 0 or close to 1. Stability gets rid of the bad rectangles. Distality gets rid of the bad points in the good rectangles. One natural question to ask is whether that's an if and only if. So if you know that you have the sort of partition that stability promises you, does that actually mean you're stable? And it's not hard to see that the answer is no. Stability and finite VC dimension they're combinatorial properties. They're about containing or omitting finite sets of points. And these statements about regularity they're fundamentally measure theoretic, or if you really don't like talking about measures and you like finite sets, they're talking about densities. So the idea is you're never going to get an exact equivalence between kind of a density theoretic property and a combinatorial property, because what you're going to do is you're going to take a very, very large thing that has the nice property. So take a very large graph with finite VC dimension, and then take a small graph with very, very big VC dimension and graft it on. And this small thing isn't going to affect your overall density. So it's just going to disappear into your error terms. But it has, so your very large thing is still going to behave like it has finite VC dimension for the purposes of things like regularity. But you have this very small set of exceptions. You have this small set with high VC dimension, and it's going to say you don't have small VC dimension. So you have these kind of problems, and you fix this by quantifying over the measure. So the equivalence is that you want not just the regularity lemma for finite VC dimension, you need it uniformly in all measures. So the equivalence you get involves this sort of complicated statement where you have to be careful about the quantifiers. And you say, E has finite VC dimension exactly when uniformly in all measures. That's what this is saying. For every epsilon, there is an M, so that for all measures. So uniformly in all measures, you look like you satisfy the VC dimension version of regularity. And you can do the same thing with stability. You're stable exactly if uniformly in all measures you satisfy stable regularity. Okay. So that's sort of the background that we were coming into this with, because in around 2000, people generalized graph regularity to hypergraph regularity. And the question we were interested in is, do these kind of nice regularity lemmas generalize to the hypergraph case, and what combinatorial model theoretic dividing line sort of properties do these nice hypergraph regularity lemmas correspond to? I'm going to focus exclusively on the partite ternary case, where E is a subset of X cross Y cross Z, except like one slide where I'll state a more general result. Things get more complicated, and we definitely want to stick to this setting just to avoid a lot of notation. So the first version of hypergraph regularity that was proven is called weak hypergraph regularity. It was proved by Chung fairly soon after Semereti's graph regularity. So I think still in the early to mid 70s. And it looks very similar. So it says now E is a hypergraph. So it's a subset of X cross Y cross Z. And for every epsilon, I should partition X and Y and Z into sets. And so now instead of rectangles, I get boxes, right? A box is an AI cross a BJ cross a CK. And then this says that except on a small number of boxes, I get this relation E is, well, weakly quasi-random. And I'm not going to say exactly what weakly quasi-random is, except it's related to the fact that this is called weak hypergraph regularity. So Chernikov and Starchenko show, kind of incidentally, because the proof doesn't, they're doing other things at the time, and the proof doesn't add that much, take that much more work than the binary proof. Well, it takes a little, that's not fair. It takes a little more work. I mean, there's something to show there. So they show that you have a version of weak hypergraph regularity for hypergraphs of finite VC dimension. What does it mean to have finite VC dimension? So if you have E is a ternary relation now, so it induces three binary relations, right? E is a subset of X cross Y cross Z. So you could think of it as a binary relation between X cross Y and Z, or between X cross Z and Y, or between X and Y cross Z. So you have finite VC dimension if each of these three relations has finite VC dimension. And they show exactly what you'd expect. They show that if you have finite VC dimension in this sense, then except on a small number of boxes, your density is close to 0 or close to 1. So if E has finite VC dimension, E is approximated by a union of of a small number of boxes. And you can do the same thing with stability. So we say a ternary relation is stable if it's stable, if the three corresponding binary relations are stable, and if your ternary relation is stable, you satisfy stable weak hypergraph regularity, which again says you have these partitions into boxes, your density is either close to 0 or close to 1 on every box. There are no exceptional boxes. We don't get converses. So there's the paper by Caroline Terry and Julia Wolf that just showed up on the archive a couple of weeks ago that I'll refer to several more times. And they point out this example. So this is the set of X, Y, Z where X is less than Y and Y is equal to Z. And they point out this is unstable because as a relation between X and Y cross Z, it's unstable. But it's kind of a trivial relation because it has density close to 0, right? It concentrates on the diagonal where Y is equal to Z. So in fact, if X, Y, and Z are large sets, you don't need to do any partitioning at all. This just has density 0 on X cross Y cross Z. There's a similar example for NIP. So you take X and Y to be, say, the unit interval 0, 1, and Z is the set of monotone functions from 0, 1 to itself. And then you take the set of X, Y, Z so that X is less than Z cross Y. And this has infinite VC dimension because you can carve out arbitrary subsets of the diagonal, but uniformly in all measures, it satisfies the finite VC dimension version of regularity. I won't get into why, but it's roughly because, yes, it has infinite VC dimension, but the failure of finite VC dimension is concentrated on the diagonal, and the diagonal has measure 0. No matter what your measure is, the diagonal always has measure 0. So this is always so you can't actually concentrate on it. So there's a notion, Artem and I have been calling this like slice-wise stable and slice-wise finite VC dimension. Terry and Wolf call it weakly stable, and weak finite VC dimension, or weak NIP is really what they say. So instead of looking at the binary relations, you look at the slices. So if you take this E as a subset of X cross Y cross Z, and you fix one coordinate in any of the three sets, now you have a binary relation. So you say that this is slice-wise stable or slice-wise finite VC dimension if if there's a uniform bound on the size of the ladders or on the VC dimension across all of these slices. And here, so for finite VC dimension, you get the equivalence that you expect. You satisfy the VC dimension, the finite VC dimension version of regularity exactly if you are uniformly slice-wise finite VC dimension. I thought this was obvious, and then I realized it is not obvious. It's not so clear that you get this in the stable case. It's probably true, but there's not. I don't know that anyone's written. Well, anyway, Taryn will ask this as a question, and I think that proof has at least not been written down yet. All right. So that's kind of the state of knowledge for weak hypergraph regularity. And why is it called weak hypergraph regularity? So I'm actually really glad. So Gabe just discussed exactly this decomposition for regularity type lemmas in his talk. So one way to think about graph regularity is to think of it as giving you a decomposition into a structured part, a quasi-random part, and then a small error part. And this way of thinking about regularity is very useful as you get into more analytic sort of ways of looking and applying regularity. So the structured part is, notice what I'm writing, this thing I've written here. Don't have this thing I'm writing here. This is a weighted sum of rectangles, right? So the structured part is the information that gives you what are your rectangles and what is the density on each of those rectangles. Then you have this quasi-random thing that tells you, well, okay, I know what the density is on each rectangle, but which specific points are present. And then typically there's going to be an error term. And the finite VC dimension regularity is really telling you that that middle term vanishes and that all those alphas can therefore be either 1 or 0 because you don't need this middle term to resolve the densities. And then you can push the intermediate rectangles into your error term. Weak hypergraph regularity gives you the same sort of decomposition. You have a structured part, which is a weighted sum of boxes, a weakly quasi-random part, and again, finite VC dimension is telling you that the middle part, the quasi-random part, vanishes, and that in the structured part, the weights are 0 or 1. And you still have this error term. It's called weak hypergraph regularity because there's a stronger version. So here's kind of the simple example of why weak hypergraph regularity isn't fully capturing the structure random distinction in a hypergraph. So take U, V, and W to be random graphs on the 3 pairs of sets. And I'm going to take my ternary relation to be the set of triples X, Y, Z, so that an odd number of the pairs belong to the corresponding graph. Right? That's what I've written here, sort of notation in a more notationally heavy way. Right? I look at the pair X, Y, I ask if that belongs to U. I look at the pair X, Z, I ask if that belongs to V. I add these all up and I ask, is that an odd number or an even number? As far as weak hypergraph regularity is concerned, this is just a quasi-random thing. There is no structure here. And we look at this and we say, well, wait, there's a lot of structure here. Right? But the structure is coming about entirely at the level of the pairs. Right? If I knew the sets U, V, and W, I would have a total description of E. But U, V, and W are themselves random. So every box looks quasi-random. So the full version of hypergraph regularity for a ternary hypergraph asks us to have both a unary and a binary structure. So there's again a unary structure, which is a weighted sum of boxes. But then also there's going to be this new binary structure, which is a weighted sum of, well, they're called cylinder intersection sets. So I have UI, UV, VJ, and WK. These are quasi-random graphs And then I can take combinations of those. The important thing about the binary structure is it's determined pairwise, right? UI looks only at XY, VJ looks only at XZ, WK looks only at YZ. So the binary, that's what we mean when we call it the binary structure. And then there's a quasi-random part, which is now actually quasi-random rather than weakly quasi-random. And there's a small margin. So good, I did define these. So the generalization of a box here is what we call a cylinder intersection set. So a binary cylinder intersection set is going to be exactly a set of this kind I've just been describing. So it's a set of XYZ where XY belongs to a specified set, XZ belongs to a specified set, YZ belongs to a specified set. It's called a cylinder intersection set because a cylinder set would be the set of XYZ so that XY belongs to A, right? We think of that as a cylinder because we take a binary set and we just cross it with the third coordinate. And then it's a cylinder intersection set because it is an intersection of three cylinders oriented in different directions. Finite VC dimension was telling us that both the truly random data, but also the binary data were disappearing. And what we would like is some analog of finite VC dimension where we keep both the unary and binary data, but we get rid of the quasi-random data. And then you could say this in sort of total generality. So if you take a D-ary relation, a relation on D tuples, full hypergraph regularity says you have a unary data and you have binary data, and you have ternary data, all the way up to D-1 ary data. And then you have a quasi-random part, and then you have error. And we'd like to just be able to cut that off anywhere, right? We would just like to say, okay, I want the quaternary data to be the most complicated thing, and the quintinary data and everything higher disappears because I have a nice combinatorial problem. All right, so Artemin, well, there was a good guess for what the property would be, which is VC 2 dimension. So I think Shala introduced this under the name like NIP2, but finite VC 2 dimension is the natural way to translate that into the combinatorial terminology. So the way I like to put this is you have finite VC 2 dimension if there's a finite tripartite hypergraph that you don't contain copies of. So you omit some small tripartite hypergraph. And this example I gave earlier, which has infinite VC dimension, because the UV and W's are are random, so they certainly have infinite VC dimension, but has finite VC 2 dimension. And there's kind of a nice quick argument to see this, which is if you think of the hypergraph that has two vertices in each part, so A, B, C are all pairs, and G contains 7 of the 8 possible triples, right? So there are 8 possible triples containing one element of A, one element of B, one element of C, and you contain 7 out of 8 of them. And you can't embed that into E, because if you just do a parity argument, and you look at what you've committed to about parities of the sets, and if you just add them up, you discover that you can't possibly contain this. That if you have an X and an X prime, and a Y and a Y prime, and a Z and a Z prime, and if 7 of the 8 edges are present, the 8th edge must also be present. All right. So what Artem and I showed is, well, the result that you might anticipate given how I've set this up. If you have finite VC 2 dimension, then there are partitions of pairs. So there's a partition of X cross Y, and a partition of X cross Z, and a partition of Y cross Z. And now, instead of looking at boxes, we look at the cylinder intersection sets. And except for a small number of exceptional cylinder intersection sets, the density is either close to 0 or close to 1. Or to say this another way, if you have finite VC two dimension, you can be approximated by a union of finitely many binary cylinder intersection sets. And equivalently, that means you can be written as a sum of the unary data plus the binary data, and then there's no quasi-random data left. There's just a little error term to account for the exceptional sets and the way that the having density close to 0 is not the same as containing no points whatsoever. All right, so I will just say there's a generalization to, you can generalize this to I've done a terrible thing and switched my D and my K from earlier. So if E is a K-ary relation, so I'm just saying it in the partite setting here. So E is a subset of x1 cross x2 up to xk, and it has slice-wise finite VCD dimension. And that means exactly what you would guess, namely, if I fix K minus D coordinates, and I look at the corresponding D, K minus D minus 1, I fix the correct number of coordinates, and I look at the corresponding D plus 1 ary relation, it emits some D plus 1 ary, some small D plus 1 ary subgraph. So these are, well, then you have a partition in which you are described by cylinder intersection sets of the appropriate complexity. Obviously, okay, that's all I'll say about that. It is the generalization you would expect, and the notation just becomes unbearably heavy as you do this, and as anyone who's actually looked at our paper.
Sorry, Henry, in the fibers, should it omit the same finite graph, or it doesn't have to omit?
No, there should be a uniform bound on the size of the graph it emits. But you just need that every fiber, there's some size, and every fiber emits some graph of that size. But it doesn't have to be the same one. All right, and this is exactly what I promised earlier that we should have, that finite VC dimension means you can approximate your K-ary hypergraph using up to D-ary data and a little bit of error, and you don't need D plus 1 ary data, and you don't need quasi-random data. And, well, and you do this uniformly under all measures. The natural question after that was, what about stable hypergraph regularity? And this turns out to be a little complicated, because it turns out it's not obvious what we mean by that. So if you kind of the first thing you might come up with is something like, well, I want to have cylinder intersection sets. So I want to partition X cross Y and X cross Z and Y cross Z in such a way that on every cylinder intersection set, rather than almost all of them, the relation has density close to 0 or density close to 1. So this is a fairly natural translation. So it says, right, exactly where weak stable hypergraph regularity had boxes, we have cylinder intersection sets. So there's kind of a first guess everyone has for what should be the excluded structure, which is, we've been calling it the half simplex, which is maybe not a great name for it, but whatever you want to call this, the set of, so instead of talking about ladders, you take something like the set of X, Y, Z in the unit box, and you take those X, Ys, and Zs so that X plus Y plus Z is less than a half, right? Or you could take think about finite substructures of this. It's not hard to show, well, it's not trivial to show. One can show, and Terry and Wolf have a proof of this. doing it in a more general way. I think for this specific example, there may be a slightly shorter proof, but one can show, and they have written down a proof, that this does not have stable hypergraph regularity. But they also point out that there's another example which doesn't look like that. And it's this example that they got to coming out of these algebraic regularity questions. And Julia, of course, was talking about this yesterday in her talk. So think about 3 points from F3 to the N. So X, Y, Z are vectors from, n length vectors where N is long from F3. So each coordinate is 0, 1, or 2, and we think of addition as being mod 3. And you take the points where you take those X, Y, Z where the first position of X plus Y plus Z, which is not a 0, is a 1, as opposed to a 2. And they show that this also does not have this first notion of stable hypergraph regularity. And they ask the natural question, which is, okay, is there some, neither of these can be the minimal combinatorial configuration whose presence is equivalent to the failure of stable hypergraph regularity. So what is there? It's not obvious that there's going to be one. And in fact, I don't quite want to claim this because we're still checking this, but I think there may be an argument that actually you can't be contained in both of these and still fail stable hypergraph regularity. So there may simply fail to be a clean combinatorial characterization of this. But on top of that, it turns out there are a lot of other things you might do. Oh no. I'm hanging on because, as they're saying in chat, they have lost audio. Yeah, the Zoom seems to be working. I don't know, anyone on Zoom have an interesting question to keep us busy while we wait for them to fix it?
Can I just ask one question in the meantime?
Please.
Hey, Henry,
Oh.
sorry.
Oh.
Having some technical difficulties.
Yeah. Is it working now?
But so I don't know if you can hear me now, but now we can't hear you, so.
Oh, I can hear you. Can other people hear me?
Yes, I can hear.
But I can't hear Henry.
Can we?
Seems like they still cannot hear us. Yeah.
Yeah, it seems like they still can't hear us.
But maybe okay. I can still ask.
Yeah, go ahead and ask your question.
Right, so
I think we should just wait for them to restart.
we have the notion of VCK dimension.
I'll tell them.
We have a reasonable notion of VCK density.
A VCK that's
Density.
yeah. Oh, do we? So I think if you write down the obvious thing, it's not, you can write down the obvious thing, and I don't know that anyone has looked into whether it behaves in a reasonable way, I think is the answer.
I see. Yeah. Okay.
I also have a question.
Yeah.
Yeah, so VC density can be stated as a number of types, right? Over finite sets.
Yeah.
Or codensity. Can do the same for K, VCK?
No idea. I have no idea. Unless Artem wants to jump in and tell me that he knows the answer, I suspect that the answer is simply not no. Yeah. So
if I can say yes, so it is considered. Not much is done about it, but it is considered in the first paper on this that I wrote with Daniel Palasin and Kota Takeuchi, called on independence. So we have some bounds there on this kind of generalized VC density.
yeah, I think there just haven't been a lot of papers on VCK, and so yeah, I think most of what's known of that kind of question is going to be you can just look at that paper that Art mentioned on independence, and it is either there or it's not known.
There is some kind of sour shala lemma.
Hello. Sorry. I hope we're not interrupting a good conversation, but apologies from the field's in-person room who disconnected.
Yeah. Okay. Can you hear me now?
Yeah. Would you mind going back a slide for us?
Not at all.
Yeah, as you were describing, right, this exact set in F3 to the n. As you were describing that, we lost you.
Okay, so let me quickly. So Sergey had just asked a question that's worth answering. Artem's answered it in chat. Yeah, there is a version of Sawyer-Shella for K dependence. It's kind of not the one that it is not the first thing you might conjecture, and in fact, that I think Shella did conjecture. But there is a Sawyer-Shella theorem for VCK. Okay, so I was saying there's the second example from this that Terry and Wolf show is also if you contain this example, you fail to have stable hypergraph regularity. And then there's a natural question: is there going to be some single minimal configuration contained in both of these? This is an open. Well, this is currently an open question to sort of exactly characterize this notion of stable hypergraph regularity. I said this question is approximately in Terry and Wolf's paper, and I'll come back to that. Because the issue is there are actually a lot of other. Actually, once you start digging into this, comparably natural notions that you might have instead called stable hypergraph regularity. So one thing I'll point out is both the examples that fail that first notion of stable hypergraph regularity from the previous slide, they're both finite VC dimension. So one thing you might look for is, and in fact, they're sort of have very simple VC dimension. So one thing you might look for is something that has a very complicated unary structure, which is to say, in particular, sort of badly fails to have finite VC dimension, but still has a simple binary structure. And there's a more complicated to write down, but actually, I think, comparably natural notion of stable hypergraph regularity, where again, you look at cylinder sets, but instead of asking to have density close to 0 or close to 1, which is kind of like saying that you're right, having density close to 0 is like having is like being close to a zero-ary relation, right? Because the empty set is a zero-ary relation. So if you say your density is close to 0, that's like saying you're close to a zero-ary relation. So if NIP things are unary, you could say, maybe I just want that on every binary set, every cylinder intersection, I'm almost unary. And so this is a much weaker stable hypergraph regularity that you might also reasonably look at. But wait, it gets worse. So Takeuchi proposed a combinatorial configuration that looks like a natural stability-like notion. You take the set of X, Y, Z. I don't know why I switched from reals to integers. So just some infinite ordered sets, right? X and Y are from an infinite ordered set, and Z is a set of monotone functions. This is the same example of Takeuchi's I mentioned earlier. And you take those triples where X is less than Z of Y. And Terry and Wolf consider the same thing, except you don't require that they be monotone. And Terry and Wolf give the first actual successful characterization lining up a combinatorial property with some notion of stable hypergraph regularity. Their notion is neither of the ones that I've already mentioned, but it is certainly a stable hypergraph regularity like notion. And so my point in general is there seems to be some sort of zoo of properties between below VC2, which is, I'm pretty sure, the weakest notion you could hope for, and that first notion I mentioned, which is probably the strongest notion you could hope for. And so there's just a question of what does this zoo look like, and how do we characterize all the principles? And I guess in particular, kind of stepping back from all this hypergraph regularity stuff, there's a question that I think is just a pure combinatorial model theory question that I'd like an answer to, which is, how will we know when we're done? How will we know when we've found them all? Just to sort of illustrate how complicated the current understanding is. So I was describing these notions in terms of how you describe approximations of E. So you say E can be approximated by boxes, or E can be approximated by cylinder intersection sets. Terry and Wolf actually have this different approach where they're looking in a more precise way at how you control what the sets of intermediate density look like. And it's not clear that they write down a bunch of notions. It's not clear they all line up to the sort of notions that I was describing. So that question they ask and the theorem they prove is not exactly the theorem I stated because they have a slightly different way of describing what stable hypergraph regularity would look like. So there's potentially a lot of notions in here. And so one question is just how will we know when we've found them all? And just to back that down to the binary level, as far as I know, stability and NIP, stability and finite VC dimension, are the only binary dividing lines of this kind. I should qualify that. There might be like some trivial ones. Like it might turn out that, being a binary relation that depends only on the X coordinate is technically a notion of this kind. When you, just like slice-wise stability and slice-wise VC dimension are probably ternary notions of this kind. But so I have not seen a theorem that says stability and finite VC dimension. There are lots of model theoretic dividing lines. So what's the theorem that says, here is the class of dividing lines that contains only stability and finite VC dimension, and we know it doesn't contain any others in the binary setting? Because we really want the generalization of this to the ternary note world, just to not be endlessly searching for examples, but be able to actually pin down what are all the examples of notions in this more complicated setting. That is the same slide. That is the end.
All right, thank you. Awesome. Are there questions from the audience?
So I have a question. So earlier on, there is a characterization of being NIP as we have such kind of a correct gap decomposition across all measure. Am I right?
Yeah.
So is there an analog of that for VCK? Or maybe you already mentioned it, but I never heard.
Yeah, so the VCK theorem, it's an equivalence for uniform slice-wise VCK dimension, or slice-wise VCK dimension is equivalent to having the appropriate regularity lemma uniformly in all measures, and that is an equivalence.
I see. Thanks.
Yeah.
Hi, Henry. So is that slice-wise VCK stuff in the paper, the preprint you guys have?
Yeah, so that is in our preprint. We just call it VC dimension. Like we take that to be the definition of K or VC dimension.
I see. I see. I guess I missed that, or we would have included it, of course.
Yeah,
Yeah. Yeah.
Yeah, I think there's some debate over what the terminology is, and then yeah, you
I
call
see.
it VC versus slicewise or versus
Weekly,
week
yeah,
VC, and
yeah.
we
Yeah,
should
I mean, that
we should
was-
agree on terminology.
Yeah,
but-
sure. Slice is a good word. Yeah. I did want to mention that, yeah, I think our formalism is like a bit different because we work with these like hereditary classes, so it's a little more syntactic.
Yeah.
But we did prove something similar about the weak/slice
Right.
VC dimension thing
Yeah.
only in the 3 uniform case.
Yeah,
but-
so yeah, I think you guys give a
yeah.
much shorter proof in the ternary case. And
mhm.
yeah, and I should mention, so I like to talk in this like measure theoretic setting where I talk about uniformly under all measures. And yeah, the Terry Wolf paper you guys have this slightly different, I think you're getting at the same idea in just the slightly different way.
Yeah, I mean, I'm sure it seems to me like they're equivalent essentially,
sure.
but like in our formalism, the stability does characterize the no irregular pairs, if that makes sense. Or yeah, but I think it's because we have this syntactic notion, so you're allowed to like pass to substructures and stuff. But yeah.
No, I think it's exactly that the way you're passing to
it's
substructures is kind of equivalent to saying
see.
uniformly under measures.
I see. Okay. Yeah. Okay. Yeah. Thanks.
Anand has a question.
Yeah, okay. Thank you, Henry. Hi, Henry. Yeah, just the only thing is this thing about stability in NIP is dividing lines that somehow appear elsewhere. That is interesting that only these dividing lines, they've appeared independently in mathematics, like in dynamics and function analysis, and no other dividing lines appear. Other things didn't appear, but they appeared. And I don't know. I mean, technically, these notions are concerned with cohers. The whole thing could be described in terms of cohers. So I don't know, finally satisfiable type. So I don't know whether this is related.
But so, for
What?
example, is there a proof
What?
that they're the only notions that could be characterized by cohers?
Yeah, I don't know. Yeah, so there should be something like this around to explain these two notions and and why they've. I mean, it's funny. The notion of simplicity is now. It's funny. I mean, the notion of simple is important. I mean, it's important for, say, even combinatorics for this regularity lemma and for this Tow's algebraic regularity lemma. You know.
Yeah.
But it's but the notion didn't appear really, except didn't you? What happened? You said that Tau proved something. Tau proved something about. He proved something about the stability of this inner product formula independently. Okay, but it was still stability. But yeah, but it's an interesting question about stability in NIP. Yeah.
And I mean, maybe maybe there's some other characterization just to make life complicated. Maybe the answer is stability, finite VC dimension, and distality are the only notions because there is a distal regularity lemma. So I don't know what the theorem is, but there should just be some theorem saying in the binary setting, there's a small list of dividing lines that are something.
Yeah, that's right.
I don't know what it is.
Good point. Nice point. Thanks.
Any other questions from either of our audience? If not, then let's thank Henry again. Thank you, Henry. All right, we'll resume tomorrow at 11? At 11, yes. And so then we'll be back. I don't know. I guess I can wait.
Thanks, Henry. That was a very, very nice talk. I don't know if he's still there. He's maybe gone.
I think understand why this is true. You understand how to understand the